In the last section, we looked at the stress-strain response and the mechanical properties of a single composite layer, but that's not all that useful. We really want to put those layers together into a useful structure, into a laminate. And so let's start out by making a couple of definitions here. A laminate is simply a structure that's made up of multiple layers, or laminae. We're going to restrict our analysis in this section to be those of a symmetric laminate. And that means that for each layer you have above the mid-thickness, the mid-plane, there's an identical layer. When identical means same thickness, same orientation, same material, at the same distance below the mid-plane. A cross-ply laminate is one that consists only of 0 and 90-degree layers. A balanced laminate means that if you have a plus theta layer, you have to have a minus theta layer with the same thickness to balance those properties out. Now, 0 and 90 degrees would not be included in that because if you think about it, a 0-degree direction or a minus 0-degree direction, well, the fiber is really in the same direction. Same thing with a 90. A plus 90 minus 90 is really the same. So if there's a plus theta layer other than 0 or 90, you have to have a minus theta layer for that to be balanced. And we'll see what the effect of that is on material response in a little bit. An angle ply means it consists only of plus and minus theta layers. And then there's a quasi-isotropic laminate. So for that, you're looking at one that has equal mechanical properties in all directions within the xy plane. Quasi-isotropic because it will be different out of the plane or in the z direction. Most likely it's going to be done with a 0, 90, plus 45, and minus 45 degree layers. And again, a lot of aircraft structures, we talked about that before, a lot of those will utilize that layup scheme because you do get, again, equal properties in all direction, and so a lot of their qualification work is based on that type of layup. So let's look at a couple of those. Here's a plus 20 and a minus 20. Well, that's an angle ply. It's also balanced, but it's not symmetric. This one with the two plus 20s is going to be symmetric. And so here we have 4 layers, and again, it's going to be balanced. You have a minus 30 for every plus 30, and it would be called an angle ply, but you notice it's not symmetric. There's a plus 30 on the top, there's a minus 30 on the bottom. If you rearrange those, so the plus 30s are on the outer edges and the minus 30s are toward the middle, that is not only balanced and angle ply, but that is a symmetric laminate. Here's one with all 0s and 90s. We call that a cross ply. And that one also is symmetric. And as we said, that makes it automatically balanced because there's nothing other than a 0 and 90 that has to be balanced with a negative of that angle. So again, we're going to start out by only looking at symmetric laminates. And what that means from a mechanics standpoint is that if we put in-plane loads on it, it's not going to bend. And so we can look at the extension, that is the in-plane behavior, and the bending behavior separately. So what's called classical lamination theory or composite lamination theory, there's a couple of assumptions. One is we're in a state of plane stress. The other is that we have perfect bonding between the layers, so the layers don't slip relative to one another. So we can look at the strains. If we pull on a laminate, and there's no bending, we assume that the strain is the same in every layer. We talk about stress resultants. In nomenclature of plates and shells, we usually talk about the stress resultants, NX, NY, and NXY. And those are just the resultants of the stresses in those directions. And those are usually given, well, they're always given, rather, in force per unit width. So it would be like pounds per inch. Therefore, if you look at, say, a pressure vessel or a plate and you know what the loading is going to be, the NX, NY, NXY are independent of the thickness. So that's your first step of design is if you know what those stress resultants are, then again you can work to find the thickness of the layer of the laminate that you want to use. So each layer we have the stress strain resultants that we looked at last time, stress strain results rather. And you notice in this case we've said, okay, we're going to call K layer K. And we're going to say the subscript on there represents the midplane, or sometimes called the membrane strain. Now, that means for our symmetric laminate that's subjected to in-plane loading, the strain is going to be the same in every layer. But when we add bending later on, of course, the strains are going to vary from top to bottom of the laminate. So again, the 0 just means it's the midplane or membrane strain. All right, so here's we've shown a few layers here. And if we look at the stresses in the x direction of every layer, you can see, well, they can be very different because the stiffness of the layers is going to be different. But our stress resultant is the resultant of those stresses. In other words, if we integrate the stresses over the thickness, that is by definition the stress resultant. Now, again, if we're just using in-plane loading, there's no bending, the stress in every layer is going to be constant. So instead of integrating, we can make that into a summation instead. So over the number of layers, if we just take the stress in the x direction, multiply it by the thickness, that is indeed the stress resultant in the x direction. Okay, so applying the stress-strain relations we looked at just a few moments ago, we can write this expression for n sub x. And again, it involves the top row of the Q-bar matrix of each layer multiplied by those strains, and then the whole thing multiplied by the thickness of that particular layer. And then we sum that over the number of layers. And we can write similar expressions for the stress resultant n sub y and for n sub xy. And so putting that all together, here's our equation for the stress resultant. So we're summing over the number of layers the Q-bar matrix times the strains times the thickness of that layer. Now, if we look at what was, we go back for just a moment, if we look at the summation here, remember that these strains are the same in every layer. So we can just look at the summation and we give it a name as the extensional stiffness matrix A. So again, we get the A matrix by simply taking the Q-bar matrix of every layer, multiply it by its thickness, and then sum those up. And that is the extensional stiffness matrix A. And since most of the time we don't start out knowing the strains, but rather we know the loadings and stress resultants, and so to find the strains, we look at the inverse of the A matrix times the stress resultants. And so I've just called these elements of the inverted A matrix, I've called them A1 1 star, A1 1, A1 2 star, etc., instead of using the negative 1, which would imply that each individual term has been inverted, but rather this is the inversion of the entire matrix. So again, when I say the A star terms, they are the terms of the inverted A matrix. So let's talk about how we would look at the laminate properties. You know, if we have a certain layup, we'd still like to know what's the effective modulus in the x direction and the y direction, what's the Poisson's ratio, etc. So let's go back and look at the average stresses in the laminate. Remember that we said the stress resultants are essentially just the stress times the thickness. So the average stresses would be just 1 divided by the total thickness times those stress resultants. Okay, and so we can rearrange that and say, okay, the stress resultants are the thickness times the average stresses. Now, also remember that the strains, we just said, are equal to the inverse of the A matrix times the stress resultants. And so you can also say then it's equal to the inverse of the A matrix times the total times the stresses, just like we have above. Now, it seems kind of a long way to get there, but we're writing those out with the inverted A matrix as shown here. We're going to compare that to the plane stress, strain stress relations in global coordinates that we looked at in the last section. And remember, that was how we ended up defining, the modulus of elasticity, the Poisson's ratios, and the shear modulus. So if we compare those, we can calculate what the effective moduli in the x, y directions and in the Poisson's ratio and the shear modulus of the laminate. Now, there are terms in the 1,6 and 2,6 that will be zero for an orthotropic or an isotropic material, and would also be zero for a balanced laminate. We're not really going to be interested in what those are, but again, they could be non-zero. But again, doing these comparisons, we would say then that A of x, modulus E of x would be 1 over the total thickness times the 1 term of the inverted A matrix. Similarly for EY. If we look at the Poisson's ratios, you can see that the thicknesses will cancel out, and so we end up with negative A1 2 star over A1 1 star. And there's the shear modulus GXY, 1 over the T total times A6 6 star. Now, that kind of sets us up for doing an example in the next class. So we're going to find the mechanical properties of a laminate, and we'll also look if it has an in-plane load. We'll be able to calculate the stresses in the laminate, or I should say the stresses in each layer of the laminate when it's subjected to that in-plane load.